Welcome to tonight's journey into the deep ocean. Please find a comfortable resting position in your bed. Allow your breathing to find a steady rhythm. Close your eyes and release the day's tension. Tonight we explore a remarkable underwater geological feature. Our destination lies far beneath the ocean surface. We are visiting the Costa Rica Vent field. This location represents the youngest known hydrothermal system. Geologists consider this site an infant in Earth time. Your mind can relax as we explore this environment. The deep sea offers a profound sense of peace. There are no sudden noises or bright flashing lights. Only the quiet rhythm of the ocean remains. Let your muscles soften into the mattress beneath you. We will begin our scientific observation very shortly. The profound silence of the deep ocean is calming. Imagine the heavy water pressing away your daily stress. The cold depths offer a perfect sanctuary for rest. Your breathing mirrors the slow currents of the abyss. Each inhale draws in the calm of the ocean. Each exhale releases tension into the dark water. The steady temperature keeps the environment perfectly balanced. There is no rush in this timeless underwater world. Geological processes unfold over thousands of quiet years. Human worries seem insignificant against this vast scale. You are safe in your comfortable resting place. Our virtual submersible protects you from the harsh elements. You can simply observe the quiet beauty below. The deep sea invites you to slow down completely. Let your consciousness drift like the falling marine snow. Our journey takes us to the eastern Pacific Ocean. This region sits off the coast of Central America. The specific coordinates are 9 degrees north latitude. The precise longitude marks exactly 86 degrees west. Surface waters here reflect the warm tropical sun. Trade winds create gentle ripples across the vast ocean. Marine traffic rarely passes through this specific sector. The nearest solid landmass is the Nicoya Peninsula. Dense coastal rainforests thrive several hundred miles away. Beneath these waves lies a hidden geological frontier. The water column here contains distinct biological zones. The epipelagic waters host abundant microscopic phytoplankton communities. These tiny plants produce oxygen for the entire planet. Mesopelagic zones introduce twilight conditions below 200 meters. Bioluminescent creatures flash briefly in the dimming light. Bathypelagic realms stretch from 1,000 meters downward. This vast midwater region seems entirely empty at first. However, delicate gelatinous organisms thrive in this open space. Abyssopelagic depths represent the final layer of our descent. This zone contains the seafloor and its unique features. This region sits above a highly active tectonic boundary. The massive Cocos Plate moves steadily eastward here. It collides directly with the adjacent Caribbean Plate. This massive collision creates a powerful subduction zone. Solid ocean crust bends under immense planetary forces. Deep oceanic trenches form along this convergence line. Friction generates incredible heat deep within the Earth. Magma chambers form deep within the Earth's mantle. Heat transfers upward through thick layers of crust. Continuous tectonic stress fractures the brittle basaltic seafloor. These geological faults provide pathways for ocean water. Seawater seeps downward through the porous rock layers. Subterranean heat sources warm this trapped ocean water. Chemical reactions alter the composition of the fluid. Minerals dissolve rapidly into the superheated liquid solution. Buoyancy forces the altered water back toward the surface. The Costa Rica vent field emerged from these cracks. Marine scientists estimate this field formed quite recently. Extreme geological youth makes this site incredibly valuable. Researchers can study the initial stages of vent formation. Most known hydrothermal fields are thousands of years old. They feature massive mineral structures built over millennia. The Costa Rica site lacks these towering ancient formations. Instead, it features small, newly formed mineral deposits. Minor earthquakes frequently reshape this volatile underwater landscape. Sensitive seismic sensors record constant low-level tectonic activity. These tremors open new fissures in the bedrock. Old fluid pathways close as the rocks shift position. The subterranean hydrothermal plumbing system constantly reroutes itself. This dynamic environment prevents large structures from forming. The ocean floor sits far below the surface. Our target depth is exactly 2,500 meters. This vast vertical distance isolates the seafloor completely. Surface weather patterns have no influence down here. Storms and hurricanes cannot penetrate this deep water. The long descent requires highly specialized submersible vehicles. Human lungs cannot withstand the conditions at this depth. Water density increases steadily with every passing meter. The bathypelagic zone gives way to the abyssopelagic zone. Temperatures drop rapidly in the upper thermocline layer. At our destination, the water is near freezing. Sensors record a constant temperature of 2 degrees Celsius. This extreme cold preserves the surrounding geological structures. The deep ocean acts as a massive thermal sink. It absorbs heat from the planet's interior slowly. Deep oceanic currents distribute this thermal energy globally. The water here originated in the distant polar regions. It sank to the ocean floor centuries ago. Slow thermohaline circulation brought it to Central America. This ancient water contains high levels of dissolved oxygen. Nutrient concentrations are also elevated in these bottom waters. Silicates and nitrates nourish the unique benthic ecosystems. The sheer volume of water overhead is difficult to comprehend. 2.5 kilometers of liquid separate us from air. This isolation creates a perfectly stable physical environment. Thermal gradients near the vents are extremely sharp. Freezing seawater meets fluids exceeding 300 degrees. This drastic temperature difference occurs within mere centimeters. Specialized thermometers measure these intense thermal boundaries precisely. The surrounding cold constantly cools the emerging hot fluids. Immense physical pressure defines this deep marine environment. The total weight of the water column is staggering. At this depth, pressure reaches 250 atmospheres. Every square inch bears thousands of pounds of force. This equals the weight of a large commercial vehicle. Unprotected objects would crush instantly under this weight. Thick titanium spheres protect the delicate scientific instruments. Water molecules compress slightly under these extreme conditions. This compression changes the physical properties of seawater. Sound waves travel much faster through this dense medium. Acoustic mapping provides detailed images of the seafloor. Sonar pulses bounce off the hard rocky surfaces. Computers translate these echoes into precise topographic maps. Chemical reactions also behave differently under high pressure. Gases remain dissolved in liquids much more easily. Carbon dioxide forms a dense liquid state here. Calcite shells dissolve rapidly in these deep waters. Only specialized organisms can construct hard protective casings. Cell membranes require unique lipid structures to function. Proteins must fold tightly to resist the crushing force. Deep sea biology has adapted perfectly to these constraints. The pressure ensures the hydrothermal fluids remain liquid. Even at high temperatures, the water cannot boil. Phase changes require much more thermal energy here. This allows superheated fluids to mix directly with seawater. Warm sunlight cannot reach this deep ocean ecosystem. The final scattered photons disappear above 1,000 meters. Absolute darkness rules this underwater landscape permanently now. No seasonal changes affect the visual environment here. Day and night lose all meaning at this depth. Plant photosynthesis is completely impossible without solar energy. Deep organisms rely on alternative chemical energy sources. High-intensity LED beams cut through the freezing water. These submersible lights reveal the hidden terrain details. Shadows stretch long and sharp across the seafloor. Suspended particles drift lazily through the artificial light. Marine snow falls continuously from the productive surface waters. These organic remnants sustain life in the barren zones. The water clarity is remarkably high near the bottom. Visibility extends for several dozen meters with proper lighting. Without our lamps, the abyss returns to blackness. Some biological light exists in this dark realm. Certain bacteria produce a faint, continuous chemical glow. Deep-sea fish use bioluminescence to communicate and hunt. However, these flashes are brief and highly localized. The overarching reality is an endless, pitch-black void. This absence of light preserves light-sensitive chemical compounds. Photochemical degradation does not occur in this environment. Organic molecules remain intact for incredibly long periods. The darkness provides a safe haven for ancient species. The surrounding seafloor presents a rugged, uneven topography. Volcanic basalt forms the foundation of this landscape. Fresh lava flows appear glassy and completely smooth. Older rock formations look dull and heavily weathered. Sediment accumulates very slowly in this specific region. Ocean currents sweep the loose particles away constantly. Deep ravines cut across the flat abyssal plains. Steep cliffs rise suddenly from the ocean floor. These vertical walls display distinct layers of ancient rock. Mineral deposits stain the basalt with vibrant colors. Iron oxides create striking patches of deep red. Thick manganese crusts coat the oldest geological structures. Bulbous pillow lavas dominate the immediate surrounding area. These rounded shapes form when hot magma meets seawater. The rapid cooling creates a solid outer crust instantly. Molten rock continues to flow inside these tubes. Eventually, the lava stops and the structures hollow out. Collapsed lava tubes create natural caves and deep crevices. Sheet flows cover flatter sections of the terrain. These flat lavas resemble dark, wrinkled asphalt roads. Small faults create sharp steps in the rock. Glassy shards litter the base of these small cliffs. Hydrothermal fluids seep through the porous basalt layers. White bacterial mats cover the warm rock surfaces. These mats look like fresh snow on dark stone. Small chimneys rise a few centimeters from the crust. They are fragile and break easily in the current. Sharp edges contrast with smooth, rounded lava lobes. The seafloor here is a dynamic, evolving environment. Geological forces continuously sculpt this hidden underwater world. Dr. Jorge Cortés led early expeditions to this region. The research vessel Atlantis floated above the Pacific Ocean. It was the early morning of April 14. The year was exactly 2018. Scientists aboard prepared for a groundbreaking geological survey. Dr. Lisa Levin led this particular oceanographic expedition. Her research team sought undiscovered geological formations underwater. They focused on the active Costa Rica margin. This region sits above a complex subduction zone. The Cocos tectonic plate slides beneath the Caribbean plate. This immense friction generates significant geothermal activity below. Researchers used multibeam sonar to map the seafloor. Sound waves bounced off the rugged ocean bottom. The returning signals painted a detailed bathymetric picture. Computers processed this data into three-dimensional topographic maps. One specific area caught the attention of the geologists. A cluster of unusual mounds appeared on the screen. These structures lacked the thick sediment of older formations. These formations looked remarkably sharp and structurally pristine. The sonar data suggested a very recent geological event. No previous expedition had documented this specific location. The coordinates were exactly 9 degrees north latitude. The longitude reading was exactly 84 degrees west. Water depth at this site measured roughly 3 kilometers. The team named this target area the Jocko Scar. They hypothesized the presence of active hydrothermal venting. Chemical sensors on a towed sled confirmed their suspicions. Instruments detected elevated levels of dissolved methane gas. Hydrogen sulfide concentrations also spiked in the water column. These chemical signatures strongly indicated nearby hydrothermal vents. The scientists needed visual confirmation of the seafloor. The human-occupied submersible Alvin sat on the deck. Engineers conducted rigorous pre-dive safety inspections that morning. The titanium pressure sphere received careful structural evaluations. Internal life support systems showed perfect operational parameters. Pilot Bruce Strickrout climbed into the narrow circular hatch. 2 geologists followed him into the cramped spherical cabin. The heavy steel hatch closed with a solid metallic thud. A massive A-frame crane lifted the submersible upward. The white submarine swung gently over the blue ocean. Thick synthetic ropes lowered Alvin into the Pacific waves. Support divers detached the heavy lifting cables manually. The submersible began its long descent to the bottom. The journey to the seafloor took 2 full hours. Inside the small cabin, the ambient temperature dropped steadily. The scientists monitored acoustic communication with the surface ship. Exterior cameras recorded the changing colors of the water. Pressure outside increased by 1 atmosphere every 10 meters. The acrylic viewports offered a limited window outside. External halogen lights pierced the deep oceanic environment. Alvin approached the target depth of 3,000 meters. The pilot adjusted the variable ballast system carefully. This maneuver slowed their vertical descent rate significantly. The submersible achieved neutral buoyancy above the seafloor. Electric thrusters pushed the vehicle forward through the water. The onboard conductivity sensors registered a sudden change. Water temperature increased by a fraction of a degree. Optical backscatter instruments detected fine suspended particulate matter. This cloudy water indicated a nearby hydrothermal plume. The pilot steered Alvin toward the source of the anomaly. The seafloor emerged from the gloom ahead of them. Fresh basaltic lava flows covered the entire area. The rock surfaces appeared glossy and completely black. Older lava formations usually accumulate a thick layer of marine snow. This particular basalt showed absolutely no sedimentary buildup. The lack of sediment proved the extreme youth of the rocks. Geologists estimated these flows erupted within the last decade. The submersible moved slowly over the jagged volcanic terrain. A shimmering effect appeared in the water ahead. This visual distortion results from mixing different water temperatures. The refractive index of the water changes with heat. The exterior lights illuminated a field of tiny chimneys. These structures measured only 20 to 30 centimeters tall. Most hydrothermal chimneys reach heights of several meters. These miniature spires represented the very beginning of vent formation. Hot mineral-rich fluids poured from the small rocky orifices. The fluid appeared completely clear instead of black. Black smokers emit dark clouds of iron sulfide particles. These young vents produced a different chemical mixture entirely. The temperature of the exiting fluid was relatively low. Sensors recorded the fluid at exactly 45 degrees Celsius. Surrounding seawater remained at a frigid 2 degrees Celsius. The sharp temperature gradient created the visible shimmering effect. The scientists documented every detail with high-definition cameras. They realized they had found an infant hydrothermal system. This was the youngest vent field ever discovered. The mineral deposits consisted mostly of white anhydrite. Anhydrite forms only at specific elevated temperature ranges. It dissolves back into seawater when the temperature drops. The presence of solid anhydrite confirmed continuous active venting. The chimneys looked incredibly fragile and structurally delicate. The pilot carefully manipulated the robotic arm outside. The titanium claw grasped a customized temperature probe. The pilot inserted the metal wand into a vent opening. Digital readouts inside the cabin confirmed the thermal data. Next, the robotic arm retrieved a specialized fluid sampler. This device is called a titanium major sampler. It captures pristine hydrothermal fluid without seawater contamination. The pilot triggered the intake valve with precision. The cylinder filled with the warm, mineral-laden water. Chemical analysis of this fluid would happen later. The geologists also observed the surrounding biological community. Mature hydrothermal vents host massive colonies of tube worms. Giant clams and blind shrimp usually dominate these ecosystems. This new vent field lacked those complex biological assemblages. Only thin mats of chemosynthetic bacteria covered the rocks. These microorganisms represent the first stage of ecological succession. They convert chemical energy into organic cellular matter. A few small squat lobsters wandered across the bacterial mats. These mobile scavengers are often the first animals to arrive. The absence of sessile organisms emphasized the field's youth. Tube worms require several years to colonize a new site. This location had not existed long enough for them. Finding such a young vent field is exceedingly rare. The ocean floor is vast and largely unexplored. Most discovered vents are hundreds or thousands of years old. Observing a nascent system provides crucial geological data. It allows scientists to study the initial stages of mineral deposition. Researchers can track how chemical compositions change over time. The biological colonization process can now be monitored from the start. This site acts as a natural laboratory for deep-sea ecology. The discovery challenged existing models of hydrothermal circulation. The heat flow measured here exceeded previous theoretical calculations. The underlying magma chamber must be remarkably close to the surface. Seismic data later confirmed a shallow melt lens below. The Alvin submersible spent 6 hours exploring the area. The team mapped the spatial distribution of the tiny chimneys. They counted over 50 individual venting orifices in one cluster. The total active area spanned roughly 200 square meters. This compact size further supported the recent formation hypothesis. The pilot eventually dropped the steel descent weights. Alvin began its buoyant return trip to the surface. The initial discovery sparked intense interest within the scientific community. Multiple research institutions organized follow-up expeditions to Costa Rica. The Schmidt Ocean Institute sent the research vessel Fokker. This expedition took place in the year 2019. They deployed the highly advanced remotely operated vehicle Sebastian. Unlike Alvin, Sebastian does not carry human passengers inside. High-bandwidth fiber optic cables connect the ROV to the ship. This tether allows unlimited dive times and real-time video transmission. Scientists controlled the vehicle from a comfortable surface laboratory. Sebastian carried an array of sophisticated new analytical instruments. A high-resolution multibeam sonar mapped the site in extreme detail. The resulting maps revealed subtle tectonic fault lines nearby. These tiny fissures provide pathways for the hydrothermal fluids. The ROV also carried an underwater mass spectrometer. This device analyzed the dissolved gases in real time. It confirmed the presence of rare helium isotopes in the water. Helium-3 is a definitive signature of deep mantle outgassing. This proved the vent fluids originated deep within the Earth. The robotic vehicle collected extensive physical rock samples. Diamond-tipped drill bits extracted solid cores from the fresh basalt. The Sebastian expedition expanded the known boundaries of the field. Researchers found several more clusters of nascent chimneys. Some of these new spires had grown slightly since the previous year. This rapid growth rate fascinated the observing geologists. Minerals precipitated out of the fluid at an astonishing pace. The ROV deployed autonomous temperature loggers around the active sites. These instruments would record thermal data for an entire year. The continuous measurements would reveal any tidal or seismic influences. The team also placed settlement plates near the active vents. These sterile plastic squares provide artificial surfaces for bacterial growth. Future expeditions will retrieve them to study microbial colonization rates. The underwater cameras captured stunning footage of the shimmering water. Powerful LED arrays illuminated the dark seafloor perfectly. The video feeds were broadcast live across the internet. Thousands of people watched the deep-sea exploration in real time. This public engagement highlighted the importance of oceanographic research. The Costa Rican government recognized the ecological value of the site. Discussions began regarding the environmental protection of this deep-sea habitat. Preserving such unique geological features is vital for future science. The location of these vents is geologically unique. Most hydrothermal systems sit squarely on mid-ocean spreading ridges. The Costa Rica Vents exist on a subducting continental margin. This tectonic setting alters the fundamental chemistry of the fluids. The subducting plate carries water-rich sediments down into the mantle. Intense pressure and heat squeeze this water out of the rocks. The expelled fluids migrate upward through complex fault networks. They leach different minerals compared to typical ridge axis fluids. Silica concentrations here are significantly higher than average. The Costa Rica Rift represents a complex tectonic boundary. It sits between the massive Cocos and Nazca plates. These massive crustal slabs are constantly pulling apart. Magma rises from the deep mantle to fill the void. This process creates new oceanic crust every single day. The rift forms part of the equatorial Pacific system. It connects to the larger Galapagos spreading center nearby. Geologists map this area using advanced sonar technology. The ocean floor here reveals deep linear fractures. These fractures guide cold seawater down into the hot crust. The tectonic forces operate at extreme oceanic depths. Pressure here reaches hundreds of atmospheres without pause. This specific rift segment exhibits unique structural features. Deep faults run parallel to the main spreading axis. These faults allow fluids to circulate deep underground. The crust is exceptionally thin in this particular region. Mantle heat easily penetrates the thin basaltic layer. This thermal transfer drives the entire hydrothermal system. The Costa Rica Rift is an intermediate spreading center. The plates separate at about 6 centimeters per year. This rate dictates the specific shape of the seafloor. Fast-spreading ridges usually form broad topographic domes. Slow-spreading ridges create deep and steep rift valleys. This intermediate rift displays a mixture of both features. A modest axial valley runs down the center line. Volcanic ridges flank this central valley on both sides. The spreading rate influences the magma chamber depth. Here, the liquid rock sits 2 kilometers below ground. This relatively shallow heat source warms the descending seawater. The steady separation rate ensures a continuous heat supply. Geophysicists measure plate movement using satellite telemetry systems. Acoustic beacons on the seafloor provide precise distance metrics. Dr. Kathleen Crane studied these intermediate spreading dynamics extensively. Her research linked spreading rates to hydrothermal vent distribution. The intermediate speed creates a highly fractured crustal environment. This location hosts the youngest known hydrothermal vent field. Geologists estimate its age at merely a few decades. Some individual chimneys formed within the last 5 years. This extreme youth offers a rare scientific baseline. Researchers observed the initial stages of mineral deposition here. Radiometric dating confirms the recent origin of these structures. Scientists use lead-210 isotopes to measure chimney growth rates. The results show incredibly rapid mineral accumulation processes. Some spires grow several centimeters in a single week. The surrounding lava flows lack typical sediment cover. Marine snow has not yet blanketed these fresh rocks. This absence of sediment confirms the recent volcanic eruptions. The youngest lava fields appear glassy and highly reflective. Over time, seawater alters this glass into dull clay. Here, the obsidian-like surfaces remain pristine and sharp. Geochemists analyze the fluid chemistry to determine system age. Young vents emit fluids with specific volatile gas signatures. High concentrations of hydrogen sulfide indicate a nascent system. Basalt is the primary rock type in this region. This dark volcanic rock forms the entire ocean floor. It erupts at temperatures exceeding 1000 degrees Celsius. Upon contacting cold seawater, the lava chills almost instantly. This rapid cooling creates distinctive pillow lava formations. Pillow lavas look like stacked, rounded boulders of stone. Their outer crust is brittle volcanic glass called pelagonite. Inside, the rock cools slowly into crystalline basalt. Sheet flows also cover large sections of the seabed. These flat plains of rock indicate high-volume eruptions. The lava poured out quickly before freezing solid. Sometimes, the fluid lava drains away beneath the crust. This leaves behind hollow tubes and fragile lava pillars. ROV Jason has navigated through these collapsed volcanic arches. Beneath the basalt lies a layer of dense gabbro. Gabbro represents magma that cooled slowly deep underground. Even deeper, the Earth's mantle consists of solid peridotite. Faulting sometimes exposes these deep rocks to the ocean. However, the Costa Rica field rests entirely on basalt. The hydrothermal fluids carry dissolved minerals from the crust. As the hot fluid hits seawater, minerals precipitate out. This chemical reaction builds the towering vent structures. Polymetallic sulfides form the bulk of these young chimneys. Pyrite, also known as fool's gold, is highly abundant. It gives the chimneys a distinct metallic yellow sheen. Chalcopyrite adds significant amounts of copper to the matrix. Sphalerite contributes zinc to the complex mineral assemblage. These metal sulfides require extremely high temperatures to form. The vent fluids here exit at 300 degrees. This temperature is perfect for precipitating heavy metal sulfides. Anhydrite is another crucial mineral in this young system. It forms from calcium and sulfate in the seawater. Anhydrite creates the initial scaffolding for new vent chimneys. It provides a porous framework for other minerals. Later, sulfides fill the gaps in the anhydrite structure. This process gradually solidifies the fragile young chimney walls. Silica also plays a role in the mineral composition. Amorphous silica coats the outer layers of older structures. The research vessel Atlantis visited this site multiple times. It serves as the mothership for HOV Alvin. Alvin is a deep-ocean submersible with titanium pressure spheres. Scientists inside Alvin observe the vents through thick viewports. Dr. Charles Fisher led several biological and geological surveys. His team mapped the exact coordinates of the field. They deployed autonomous temperature loggers into the active vents. These instruments recorded steady thermal output over many months. ROV Jason also conducted extensive robotic surveys here. Its high-definition cameras captured the glassy lava surfaces. Jason collected precise rock samples using hydraulic manipulator arms. Geologists on the surface analyzed these fresh basalt samples. They used mass spectrometers to determine exact chemical compositions. Dr. Lisa Levin studied the mineral-microbe interactions nearby. The expedition utilized multibeam sonar to map the topography. This produced a detailed three-dimensional model of the rift. The resulting maps show precise fault lines and fissures. Scientists matched these fissures to the young vent locations. The plumbing system beneath the vents is highly complex. Seawater penetrates down through a network of microscopic cracks. It travels kilometers deep into the hot oceanic crust. The water heats up and expands significantly in volume. This expansion drives the fluid back toward the surface. Along the way, it strips minerals from the rocks. The fluid becomes highly acidic and rich in metals. It loses all its oxygen during these deep reactions. The buoyant fluid rises rapidly through vertical fault zones. It eventually breaches the seafloor at the vent sites. The exit velocity of the fluid is remarkably high. Some vents discharge water at 2 meters per second. This high flow rate prevents the chimneys from clogging. The subsurface pathways constantly shift due to tectonic stress. Earthquakes can suddenly close an active fluid channel entirely. New channels open up just as quickly nearby. This causes the vent locations to migrate over time. The youngest vents often appear along newly formed faults. Researchers track these fluid pathways using chemical tracers. The chemical makeup of the young basalt is fascinating. It contains trace elements like barium and rare earths. These elements wash into the ocean during hydrothermal venting. Scientists measure these trace elements to track ocean currents. The young crust also traps volatile gases like helium. Helium-3 is a primordial isotope from the Earth's mantle. The Costa Rica Vents release significant amounts of helium-3. This confirms the deep mantle origin of the heat. Carbon dioxide is also abundant in the vent fluids. The gas bubbles continuously from the fresh lava fractures. This dissolved carbon supports unique chemical reactions deep underwater. The fresh rock acts as a massive chemical filter. It removes magnesium from the seawater entirely during heating. The returning vent fluids contain zero dissolved magnesium ions. This specific chemical signature proves the water reached depth. Geochemists rely on this magnesium anomaly for their calculations. The young age of the field simplifies these chemical models. Older fields have complex, reworked mineral layers to consider. Mapping this young vent field requires incredible precision. Researchers use autonomous underwater vehicles for detailed surveys. The AUV Sentry glides silently above the jagged seafloor. It carries downward-facing sonars and high-resolution digital cameras. Sentry flies just 5 meters above the active chimneys. Its sensors detect microscopic changes in water temperature. The vehicle maps the exact distribution of hydrothermal plumes. These plumes drift horizontally on deep ocean bottom currents. Sentry's data helps scientists pinpoint undiscovered vent spires. The resulting bathymetric maps possess precise centimeter-level resolution. They reveal the chaotic surface of the young lava. Fissures less than a meter wide become clearly visible. Scientists study these maps to understand tectonic stress patterns. The orientation of the cracks indicates the crustal tension. Most fractures align perpendicular to the main spreading direction. This geometric pattern is typical for intermediate spreading centers. The visualization tools allow virtual exploration from the surface. Geologists can rotate the 3D models on their computers. The Costa Rica field will not remain young forever. The chimneys will eventually grow massive and unstable. Gravity will cause the tallest spires to eventually collapse. Fallen chimneys create mounds of mineral-rich sulfide debris. Over centuries, these mounds grow into massive geological deposits. The heat source below will eventually migrate or cool. When the magma chamber solidifies, the hydrothermal circulation stops. The towering mineral chimneys will become cold and dormant. Ocean currents will slowly erode the fragile sulfide structures. Oxygen in the seawater will oxidize the metallic minerals. The bright yellow pyrite will turn into rusty iron. Thick layers of marine sediment will cover the ruins. The once active field will blend into the abyssal plain. However, the tectonic plates will continue their steady separation. New magma will rise to form fresh ocean crust. New faults will inevitably fracture the cooling basalt rock. Seawater will find new pathways down into the heat. Another young vent field will emerge along the rift. The Costa Rica vent field reveals a rugged volcanic terrain. This geological site represents the youngest hydrothermal system known. Fresh basalt formations dominate the ocean floor architecture here. Mineral deposits create a complex network of towering structures. Scientists from the Woods Hole Oceanographic Institution mapped this area. The research vessel Atlantis deployed advanced sonar to scan the crust. High-resolution bathymetry shows a landscape shaped by violent tectonic forces. Towering black smokers emerge from the fractured basaltic crust. These chimneys vent dark, mineral-rich fluids into the ocean. Temperatures inside these structures reach up to 400 degrees. The surrounding seawater remains at a frigid 2 degrees Celsius. This extreme thermal gradient causes immediate mineral precipitation. Iron and sulfur combine to form fine particulate matter. These dark particles create the illusion of thick black smoke. Dr. Susan Humphreys analyzed the mineralogy of these specific chimneys. The dark plumes contain high concentrations of dissolved metals. Copper, zinc, and iron sulfides dominate the chemical signature. Submersible Alving collected fluid samples directly from the vent orifices. Titanium syringes capture the superheated liquid before it mixes. Isotope analysis reveals the subterranean journey of this seawater. Water penetrates deep into the crust through microscopic fissures. Magma chambers heat the fluid to supercritical temperatures. The heated water strips minerals from the surrounding volcanic rock. Some black smoker chimneys here reach 10 meters in height. These sulfide structures grow at remarkably fast geological rates. Precipitating minerals can add several centimeters to a chimney daily. ROV Jason recorded a growth rate of 5 centimeters weekly. The structures remain highly fragile despite their massive appearance. Strong ocean currents frequently cause the taller spires to collapse. Fallen chimneys create a foundation of mineral-rich debris below. New vents quickly form over the ruins of older structures. White smokers present a distinctly different physical and chemical profile. These vents release fluids at slightly lower temperature ranges. Thermometers record white smoker fluids between 200 and 300 degrees. The lighter color originates from different precipitating chemical compounds. Barium, calcium, and silicon dominate the white smoker emissions. Silica precipitates create pale, ghostly towers along the seafloor. These structures often form on the periphery of the main field. The fluid flow here appears less turbulent than black smokers. Anhydrite is a primary structural component of the white chimneys. This calcium sulfate mineral only forms at elevated temperatures. When the vent ceases flowing, the anhydrite slowly dissolves away. This dissolution makes inactive white smokers extremely rare discoveries. The Costa Rica margin provides perfect conditions for anhydrite preservation. Researchers measure significant amounts of dissolved methane in these plumes. Hydrogen sulfide concentrations remain lower here than in black smokers. Dr. Charles Fisher documented the distinct fluid chemistry variations. Cross-sections of recovered chimneys reveal complex internal plumbing systems. A central conduit channels the hottest fluids upward. The inner walls consist primarily of solid metallic chalcopyrite. This copper iron sulfide lines the most extreme thermal zones. Outer layers feature a porous matrix of sphalerite and pyrite. Cold seawater permeates the exterior walls of the mineral structure. This mixing creates microscopic chemical gradients within the chimney wall. Minerals continuously deposit along these internal temperature boundaries. Radiometric dating confirms the extreme youth of this vent field. Lead isotopes indicate formation within the last 20 years. This makes the Costa Rica site a crucial geological laboratory. Scientists can observe the initial stages of hydrothermal system development. Older vent fields often mask their foundational geological processes. Here, the pristine basalt lacks deep sediment accumulation. The exposed rock provides clear evidence of recent volcanic activity. Seismic monitors detect frequent microearthquakes beneath the crust. The site sits near a complex tectonic plate boundary. The Cocos Plate subducts beneath the Caribbean Plate nearby. This specific location experiences intense crustal spreading and fracturing. Magma rises close to the seafloor surface through these fractures. The shallow magma chamber drives the intense hydrothermal circulation. Geophysicists measure the heat flow using specialized deep-sea probes. The thermal output here exceeds older Pacific vent systems. This energy fuels the rapid construction of the mineral chimneys. Expedition teams utilized the autonomous vehicle Sentry for mapping. Sentry flew 50 meters above the jagged volcanic terrain. Multibeam sonar generated a precise topographic map of the field. The data revealed over 40 distinct active venting structures. These chimneys align along a central geological fault line. The linear arrangement indicates a deep subterranean fissure system. Researchers identified 3 main clusters of intense hydrothermal activity. Each cluster exhibits unique morphological and chemical characteristics. The depth of this vent field creates immense hydrostatic pressure. Ambient water pressure here exceeds 200 standard atmospheres. This crushing pressure prevents the superheated vent fluids from boiling. The water enters a unique supercritical physical state. Supercritical fluids possess properties of both liquids and gases. They can dissolve metals with remarkable chemical efficiency. This solvent power explains the massive mineral deposits found here. Thermocouple probes carefully measure the fluid density at the orifice. Not all venting occurs through towering mineral chimneys. Extensive areas of diffuse flow surround the main smoker complexes. Warm water seeps gently through cracks in the basaltic floor. These diffuse fluids range from 10 to 40 degrees Celsius. Subsurface mixing with cold seawater reduces their initial high temperatures. The diffuse flow zones cover hundreds of square meters. Shimmering water distorts the visual field above these warm cracks. Chemical sensors detect elevated levels of dissolved hydrogen and methane. The rapid cooling of vent fluids triggers immediate mineral precipitation. Different metals drop out of solution at specific temperature thresholds. Copper sulfides precipitate first within the hottest central conduits. Zinc and iron compounds solidify as the fluid moves outward. This sequential precipitation creates distinct mineralogical zoning within the chimneys. Geologists use these zones to reconstruct past thermal conditions. A sudden drop in temperature alters the chimney composition entirely. The Costa Rica vents show highly variable temperature histories. Sampling these fragile structures requires extreme precision and care. ROV manipulators employ titanium jaws to break off chimney pieces. The robotic arms must avoid crushing the delicate mineral matrix. High-definition cameras guide the pilots during the sampling process. Recovered samples go into insulated bioboxes for the ascent. Maintaining the ambient temperature preserves specific sensitive chemical compounds. Shipboard laboratories immediately process the minerals upon recovery. X-ray diffraction reveals the exact crystalline structure of the samples. Some chimneys feature large horizontal overhangs called flanges. These mineral shelves trap pools of superheated buoyant water underneath. The trapped fluid creates a perfect mirror reflecting the seafloor. Temperatures beneath the flanges often exceed 300 degrees. The fluid eventually spills over the edge and flows upward. This upward flow deposits minerals on the upper flange surface. The flanges grow outward horizontally over the surrounding basalt. They create complex multi-tiered structures resembling underwater pagodas. The Costa Rica field contains unusually high concentrations of iron. Massive mounds of iron oxide surround the active venting areas. These rust-colored deposits form as the iron oxidizes in seawater. The iron mounds can reach thicknesses of several meters. Core samples reveal alternating layers of different iron mineral phases. These layers document fluctuating oxygen levels in the deep ocean. Geochemists analyze these cores to understand historical ocean chemistry. The iron acts as a chemical sponge for rare earth elements. Hydrothermal fields undergo a predictable life cycle of development. The Costa Rica site currently sits in the juvenile phase. Heat output remains at its theoretical maximum for this depth. Mineral deposition outpaces the natural forces of chemical dissolution. Eventually, subterranean mineral deposits will clog the main fluid pathways. The fluid flow will shift to new fractures in the crust. This process causes older chimneys to cool and slowly crumble. Researchers continuously monitor the site to document these structural shifts. The violent expulsion of fluids generates distinct acoustic signatures. Hydrophones placed near the vents record a constant low-frequency rumble. The sound originates from fluid turbulence and mineral precipitation. Different chimney shapes produce slightly different acoustic frequencies. Acoustic engineers use this data to calculate fluid velocity. The black smokers produce a deeper resonance than white smokers. These soundscapes provide continuous data between physical submersible dives. The acoustic monitoring network operates independently for months at a time. Geologists compare this young field to the mature Endeavour segment. Endeavour features massive sulfide structures built over thousands of years. The Costa Rica chimneys are slender and highly fragile by contrast. Their chemical purity reflects the lack of underlying sediment layers. Other vent fields push fluids through thick layers of mud. That sediment alters the fundamental chemistry of the emerging fluids. The pristine basalt here preserves the original magmatic chemical signature. This makes the site invaluable for baseline geochemical research. Recent expeditions employed laser scanning to map the chimney surfaces. The lasers generate point clouds with millimeter-scale spatial resolution. This microbathymetry captures the exact texture of the mineral deposits. Scientists use these dimensional models to calculate total mineral volume. The models also track the structural degradation of inactive spires. Comparing annual scans reveals the precise rate of geological change. The data confirms the rapid evolution of this young system. Virtual reality allows geologists to explore the models from shore. Trace amounts of precious metals exist within the sulfide matrix. Gold and silver precipitate at very specific temperature gradients. These metals concentrate in the inner walls of the black smokers. Assay results show elevated gold levels compared to older fields. The rapid cooling traps the gold before it can disperse. Economic geologists study these deposits to understand terrestrial mining sites. Ancient massive sulfide deposits on land formed exactly like this. The deep ocean provides a live view of ore formation. The physical structure extends far below the visible ocean floor. The Costa Rica margin hosts the youngest known vent field. Tectonic forces recently fractured the seafloor in this specific region. Fresh fissures allow seawater to penetrate the upper basaltic crust. The fluids returning to the ocean are chemically quite unique. This pristine environment offers a rare geochemical baseline for scientists. Sensors on the ROV Jason measure the fluid pH continuously. The water here is surprisingly alkaline for a hydrothermal system. Readings show a pH hovering around 7.5 exactly. Most global vent fields are highly acidic by direct comparison. The East Pacific rise vents often drop below pH 3. The neutral pH here indicates a very young geological reaction. The basaltic rocks have not yet fully altered the seawater. In 2018, the submersible Alvin visited these coordinates. Marine geochemist Dr. Victoria Orphan collected several fluid samples here. She used isobaric gas-tight samplers to preserve the deep pressure. The titanium cylinders captured the pristine chemical signature perfectly intact. Salinity levels at the Costa Rica Vents present a complex puzzle. The expelled fluids show remarkably low chloride concentrations overall. This freshening effect comes from deep mineral dehydration processes underground. The subducting Cocos plate carries clay minerals downward into the mantle. High pressure and intense heat squeeze freshwater from these clays. This expelled freshwater dilutes the rising hydrothermal fluid significantly. Salinity here is only 32 practical salinity units. Standard ocean water typically measures 35 practical salinity units. Hydrogen sulfide drives the biological engine of this deep ecosystem. Chemical sensors detect sulfide at 12 millimoles per fluid kilogram. This concentration is exceptionally high for such a young seep. Down here, this dissolved gas acts as a vital energy currency. The sulfide originates from sulfate reduction within the buried sediments. Microbes deep within the crust facilitate this complex chemical conversion. Methane bubbles silently escape from the newly fractured basaltic rock. A laser spectrometer measures the dissolved methane gas in real time. Concentrations reach up to 40 millimoles per liter of fluid. This is significantly higher than the Guaymas Basin hydrothermal vents. The methane forms through thermogenic breakdown of ancient organic matter. Buried sediments experience intense heat from the constant tectonic friction. Carbon molecules snap apart to form simple methane gas compounds. Scientists compare this specific site to the Marianas Trench vents. The Marianas vents expel highly oxidized fluids into the ocean. The Costa Rica fluids are strongly reducing in their chemistry. Researchers also look at the Lost City hydrothermal field carefully. Lost City features massive calcium carbonate chimneys and high pH. The Costa Rica Vents lack these towering carbonate mineral structures. Instead, fluids seep gently through low-lying, flat mineral crusts. The research vessel Atlantis deployed a deep CTD rosette instrument. The rosette measures conductivity, temperature, and depth simultaneously. Water samples from the plume reveal dissolved trace metal concentrations. Iron and manganese concentrations remain surprisingly low in this field. Older vent fields normally export massive, dark iron particle plumes. The lack of iron confirms the extreme youth of this system. The underlying rocks have not yet degraded completely from heat. Fluid temperatures dictate the chemical reactions below the ocean floor. Thermocouple probes record the vent water at 90 degrees Celsius. This is considered a strictly low-temperature hydrothermal fluid system. Black smokers elsewhere routinely reach 400 degrees Celsius. The moderate heat prevents the precipitation of heavy metal sulfides. This creates a clear, shimmering fluid rather than dark smoke. Researchers analyze the stable isotopes within the collected vent fluids. Carbon-13 ratios help identify the precise origin of the methane. The isotopic signature points to a deep, hot thermogenic source. Helium-3 isotopes indicate a direct connection to the Earth's mantle. The mantle signature is faint but definitively present in the data. It proves the fluids circulate deep within the fractured crust. The Middle America Trench actively shapes this unique chemical environment. The oceanic plate bends and cracks as it subducts downward. Cold seawater flows into these fresh, deep tectonic fault lines. The water reacts chemically with the exposed upper mantle rocks. Serpentinization occurs within the newly exposed peridotite mineral layers. This specific reaction generates both ambient heat and hydrogen gas. The dissolved hydrogen further fuels the local microbial biological communities. Long-term benthic landers monitor the chemical output of the vents. Deep-sea instruments record geochemical data every 15 minutes for a year. The time series data shows chemical pulses linked directly to ocean tides. Lunar gravity subtly squeezes the porous seafloor crust from above. This physical pressure forces more methane out during low tide. Scientists expect this chemical profile to change significantly over time. As the vent field ages, the underlying rocks will alter. The pH will likely drop as acidic minerals slowly dissolve. Iron concentrations will increase as the basaltic crust degrades further. Observing this young field provides a truly rare scientific baseline. It represents a perfect snapshot of hydrothermal system geological birth. The ambient seawater here contains very little dissolved oxygen gas. The region sits within a pronounced oceanic oxygen minimum zone. Dissolved oxygen drops below 20 micromoles per kilogram of water. The expelled vent fluids themselves are completely anoxic by nature. When the fluids mix with seawater, sharp chemical gradients form. These microscopic gradients support highly diverse chemosynthetic bacteria colonies. Dissolved silica provides another vital clue about the fluid history. The Costa Rica fluids contain elevated dissolved silica chemical compounds. Concentrations hover around 3 millimoles per liter of sampled water. Silica solubility depends heavily on subsurface geological fluid temperatures. The quartz geothermometer estimates a reaction temperature of 200 degrees. The fluid cools significantly before finally reaching the ocean floor. Researchers compare this to the Endeavour segment of the Juan de Fuca Ridge. Endeavour fluids are highly enriched in toxic heavy metal isotopes. Lead and cadmium are virtually absent in the Costa Rica fluids. The pristine nature of this young fluid remains scientifically remarkable. Total alkalinity measurements reveal a very high chemical buffering capacity. The vent fluids contain abundant dissolved bicarbonate molecular ions. This specific chemistry prevents rapid shifts in the local pH. The magnesium anomaly of this site requires careful scientific examination. Typical hydrothermal fluids usually contain absolutely zero dissolved magnesium ions. Standard seawater holds about 53 millimoles of magnesium per kilogram. The Costa Rica fluids show depleted but non-zero magnesium levels. This indicates an incomplete chemical reaction with the host rock. It confirms the rapid transit time of the rising fluids. Trace elements act as highly precise geochemical fluid pathway tracers. Lithium levels are slightly elevated compared to the surrounding seawater. Boron isotopes show a distinct and measurable sedimentary rock signature. This proves the fluids pass through the subducting sediment layer. Dr. Eric Cord studied these specific chemical pathways in detail. His team mapped the fluid expulsion rates across the margin. They utilized the ROV Sebastian from the Schmidt Ocean Institute. The 2017 expedition revealed new chemical seep locations. Fluid flow rates vary dramatically across the young vent field. Some fissures release fluids at 10 centimeters per second. Other areas show a slow, diffuse chemical seepage through mud. A mass spectrometer on the ship analyzes the collected samples. A gas chromatograph separates the complex volatile organic chemical compounds. Researchers measure the exact ratio of ethane to dissolved methane. This ratio helps confirm the thermogenic origin of the gases. Propane and butane are also detected in trace chemical amounts. These heavier hydrocarbons indicate intense heat acting on buried carbon. The chemical environment here is less extreme than black smokers. However, it provides an incredibly stable energy source for life. Calcium concentrations in the vent fluid present another interesting anomaly. Calcium levels are slightly lower than the surrounding ambient seawater. This suggests calcium is precipitating out below the ocean floor. It forms subsurface carbonate veins within the fractured basaltic crust. This process slowly seals the older fluid pathways over time. The fluids must constantly find new fractures to escape upward. This explains the shifting nature of the active vent locations. Potassium levels in the fluid are enriched by 50%. This enrichment comes from the alteration of deep clay minerals. Strontium isotopes provide a secondary method for dating the fluids. The strontium-87 ratio matches the signature of the oceanic crust. It confirms the fluids interact heavily with the volcanic basalt. Dissolved organic carbon is also analyzed in the laboratory on board. The fluids contain unique organic molecules synthesized by deep heat. Formate and acetate are present in very low, measurable concentrations. These simple organic acids feed the microbial communities living below. It represents an abiotic synthesis of organic matter from rocks. Nitrogen compounds play a crucial role in this chemical ecosystem. Ammonium concentrations reach up to 2 millimoles per fluid liter. The ammonium comes from the thermal breakdown of sedimentary nitrogen. Nitrate is completely absent from the expelled hydrothermal vent fluids. The reducing environment destroys any oxidized nitrogen compounds very quickly. Phosphorus is another limiting nutrient in this deep ocean environment. The vent fluids carry trace amounts of dissolved phosphate ions. The complex interplay of these chemicals creates a unique habitat. Every mineral and gas shapes the biological potential found here. The lack of toxic metals allows delicate organisms to thrive. The high methane fuels specialized symbiotic bacteria in tube worms. The abundant sulfide supports thick mats of free-living bacterial colonies. The neutral pH prevents the dissolution of fragile calcium shells. Clams and mussels can build their shells with remarkable ease. In acidic vent fields, these shells would simply dissolve away. The Costa Rica Vents offer a gentle chemical refuge offshore. The fluid density is slightly lower than the surrounding seawater. This causes the shimmering water to rise slowly upon exiting. The Costa Rica margin hosts highly unusual biological communities. These habitats represent the youngest known hydrothermal vent fields. Tectonic subduction creates unique fluid emission profiles right here. Warm fluids seep through fractured rocks at Joko Scar. The depth measures precisely 1,728 meters below sea level. Dr. Lisa Levin led multiple expeditions to this site. Her team utilized the human-occupied vehicle Alvin in 2009. They discovered a rare hybrid ecosystem of vents and seeps. Biological assemblages here blend species from both extreme environments. Thick microbial mats cover the freshly exposed basaltic crust. These bacterial colonies form the foundation of the local food web. White filaments of Beggiatoa bacteria stretch across the rocks. They oxidize hydrogen sulfide emerging from the young fissures. The microbial mats reach thicknesses of up to 4 centimeters. Orange patches indicate the presence of iron oxidizing bacterial strains. Researchers measured microbial biomass at 50 grams per square meter. This density provides abundant nutrition for countless grazing organisms. The bacteria synthesize organic carbon without any solar energy. Chemosynthesis drives the entire biological engine of this vent field. Giant tube worms dominate the immediate vicinity of active fluid flow. The species Riftia pachyptela forms dense bushes on young basalt. Their white chitinous tubes contrast against the dark volcanic rock. Bright red plumes extend from the tops of these tubes. The plumes absorb hydrogen sulfide and oxygen from the water. Hemoglobin molecules in their blood transport these vital chemicals. Specialized internal organs called trophosomes house billions of symbiotic bacteria. The bacteria convert the toxic sulfides into usable cellular energy. Tube worms lack a mouth or digestive tract entirely. They rely completely on their microscopic internal partners for survival. Growth rates for Riftia here reach 80 centimeters per year. This represents the fastest growth of any known marine invertebrate. A second tube worm species called Lamellobrachia bahami also thrives here. These worms prefer slightly cooler fluid emissions near the periphery. Their roots extend deep into the sediment to extract sulfides. Lamellobrachia grow much more slowly but live for several centuries. Scientists recorded tube worm densities exceeding 400 individuals per square meter. This staggering population density creates complex three-dimensional habitats. Other small organisms seek shelter within the tangled tube worm thickets. Vast mussel beds surround the central tubeworm clusters. The species Bathymodiolus thermophilus colonizes the fractured rocky substrates. These bivalves anchor themselves to the basalt using strong byssal threads. They position their shells directly over low-temperature fluid flows. Water temperatures in the mussel beds average 8 degrees Celsius. Like the tubeworms, these mussels host chemosynthetic bacteria in their gills. However, Bathymodiolus retain a fully functional digestive system. They can filter feed on suspended organic particles if necessary. This dual feeding strategy ensures survival during fluctuating fluid emissions. Researchers mapped mussel beds covering hundreds of square meters. Population densities often reach 1,000 individuals per square meter. Total biomass in these beds exceeds 10 kilograms per square meter. Large white clams populate the softer sediments nearby. The species Calyptargina pacifica burrows partially into the mineral-rich mud. Their highly specialized foot extends downward into the sulfide zone. They pump sulfide-rich fluids up into their gill tissues. Symbiotic bacteria within the gills process the chemicals into food. Clam trails mark the sediment as they continuously migrate. They constantly search for optimal chemical concentrations in the mud. A highly specialized crustacean inhabits the Costa Rica margin. The yeti crab Kiwa puravida represents a remarkable endemic species. Biologist Andrew Thurber formally described this unique creature in 2011. These crabs possess elongated claws covered in dense white setae. The bristle-like setae serve as farms for epibiotic bacteria. The crabs position themselves near active methane and sulfide seeps. They rhythmically wave their arms through the chemical-rich water. This dancing motion bathes their bacterial gardens in fresh nutrients. The bacteria multiply rapidly on the surface of the setae. The crab later harvests these bacteria using specialized mouth appendages. This specific behavior represents a rare form of deep-sea agriculture. Kiwa puravida occurs absolutely nowhere else on the planet. They aggregate in high densities around specific fluid emission points. Scientists observed up to 30 crabs per square meter. Their white bodies stand out clearly against the surrounding mussels. They prefer water temperatures around exactly 12 degrees Celsius. The discovery of this species redefined our understanding of vent ecology. It clearly demonstrated active farming behavior in a deep-sea invertebrate. A diverse array of mobile predators patrols the vent periphery. Pink vent fish called Zoarcidae weave through the tubeworm bushes. They prey on small crustaceans and expose tubeworm plumes. Blind brachyuran crabs scavenge for fallen organic debris. The species Bythagria thermodron dominates the crustacean predator guild. They possess specialized mouthparts for crushing small shells. Squat lobsters of the genus Munidopsis cling to vertical rock faces. They wait patiently for drifting organic matter or small prey. Deep-sea octopuses occasionally visit the vent site to hunt crabs. The species Volcanoctopus hydrothermalis navigates blindly using sensitive tactile receptors. Limpets and snails graze heavily on the thick microbial mats. The gastropod Lepidodrylus elevatus occurs in massive numbers here. Researchers counted over 50,000 limpets per square meter. They scrape the basalt clean with their microscopic radula teeth. Scale worms dart rapidly between the various mussel shells. The species Branchipollino sympatrica lives directly inside the mussel mantle cavities. This symbiotic relationship borders on parasitism in many observed cases. The worms steal food particles filtered by the host mussel. The Costa Rica vent field supports extraordinary biological mass. Total ecosystem biomass rivals that of tropical rainforests. Carbon fixation rates here exceed those of most shallow marine environments. The young age of the vent field influences this productivity. Fresh geological fractures provide unhindered pathways for chemical fluids. This abundant energy supply fuels rapid biological colonization. Scientists measure biomass in grams of carbon per square meter. The central vent areas yield over 3,000 grams. This represents a stark contrast to the surrounding deep ocean floor. The background abyssal plain supports less than 1 gram. The vent community creates an isolated oasis of extreme abundance. Biomass decreases sharply with distance from the fluid emissions. A gradient of species distribution radiates outward from the center. Highly temperature-tolerant species occupy the innermost active zones. Filter feeders and scavengers dominate the cooler outer rings. The entire biological community spans roughly 200 meters across. This compact footprint contains millions of individual organisms. The dense concentration of life creates intense competition for space. Endemism rates at the Costa Rica vents remain exceptionally high. Many species evolved specifically for this hybrid seep vent environment. The unique geological setting drives rapid evolutionary adaptation. Fluid chemistry here differs significantly from mid-ocean ridge vents. High concentrations of both methane and hydrogen sulfide are present. This dual chemical signature supports highly diverse microbial communities. The microbes in turn support a wider variety of symbiotic animals. Researchers identified 12 new species during the 2009 Alvin dives. Genetic analysis reveals connections to both Pacific vents and seeps. The site acts as an evolutionary stepping stone between habitats. Dr. Victoria Orphan studied the specific microbial genetics right here. Her research revealed novel metabolic pathways in the local bacteria. These specific microbes can process methane and sulfate simultaneously. The animals hosting these microbes gain a distinct survival advantage. They can utilize multiple chemical energy sources from the fluids. This metabolic flexibility ensures survival as the young vent evolves. Fluid emission rates often fluctuate wildly in new vent systems. The endemic fauna possess high tolerance for environmental instability. Detailed study of these communities requires advanced robotic technology. The remotely operated vehicle Jason conducted extensive surveys here. High-definition cameras captured the spatial distribution of all species. Lasers mounted on the vehicle provided precise distance measurements. Scientists used these tools to calculate exact population densities. The submersible Alvin also collected physical specimens for laboratory analysis. Robotic manipulator arms gently retrieved fragile tube worms and yeti crabs. Titanium syringes extracted water samples from directly within the animal clusters. Temperature probes recorded thermal gradients across the biological communities. The data revealed a highly structured ecosystem based on temperature. Mussels occupy the 5 to 10 degrees Celsius zones. Tube worms dominate the 10 to 20 degrees Celsius regions. Microbial mats thrive in areas exceeding 20 degrees Celsius. Biologists also deployed colonization blocks on the seafloor. These artificial substrates monitor the settlement of new larvae. The blocks remain underwater for a full calendar year. Subsequent retrieval shows rapid colonization by microscopic vent organisms. This proves the high dispersal rate of local biological communities. Energy transfer within this ecosystem operates with remarkable efficiency. Chemosynthetic bacteria form the absolute base of the food web. Primary consumers include the symbiotic tubeworms and grazing limpets. Secondary consumers consist of predatory crabs and small vent fish. Top predators include the transient octopuses and large scavengers. Very little organic matter escapes this tightly bound biological loop. Dead organisms are rapidly consumed by specialized scavenging amphipods. Bacterial decomposition breaks down any remaining biological material. The resulting chemicals re-enter the local nutrient cycle immediately. This closed-loop system maximizes the use of available energy. Isotope analysis confirms the origin of all carbon within the animals. Carbon-13 signatures match the local hydrothermal fluid emissions. No significant nutritional input comes from the distant ocean surface. The community functions completely independently of solar energy. This independence allows life to thrive in absolute darkness. The Costa Rica field provides a perfect model of chemosynthetic ecology. Researchers continue to map the complex trophic interactions here. Every new expedition reveals deeper layers of ecological complexity. The Costa Rica vent field remains in a state of continuous flux. Its young geological age guarantees future environmental changes. Mineral deposits gradually accumulate around the active fluid vents. The Costa Rica vent field represents a biological anomaly. This ecosystem is the youngest known hydrothermal marine environment. Tectonic shifts created these fractures merely a few decades ago. Scientists estimate the field formed around 1998. Most global vent ecosystems have existed for several millennia. This recent formation offers a unique evolutionary snapshot. Biologists observe primary succession occurring in real time. The lack of established sediment alters biological settlement patterns. Organisms must attach directly to bare, fresh basaltic rock. Hov Alvin surveyed this fresh terrain in 2005. Dr. Lisa Levin noted the absence of mature microbial mats. Instead, pioneer bacterial species dominate the exposed mineral surfaces. These microbes form the absolute foundation of a complex web. They rely entirely on chemical energy from the Earth's crust. Sunlight has never reached this depth of 2,400 meters. Photosynthetic food webs depend entirely on incoming solar radiation. Here, chemosynthesis drives all biological productivity and cellular growth. Vent fluids carry high concentrations of toxic hydrogen sulfide. Methane gas also bubbles from the newly fractured seafloor. Specialized bacteria oxidize these chemical compounds continuously for energy. This oxidation process releases energy for essential cellular functions. Microbes use this chemical energy to fix dissolved carbon dioxide. They convert inorganic carbon into usable organic sugar molecules. This mechanism mirrors terrestrial plant photosynthesis on the surface. However, these chemical reactions operate at absolute zero visible light. The energy transfer efficiency here is remarkably high and stable. Chemosynthetic production rates exceed those of many coastal marine estuaries. Researchers measured carbon fixation during the 2017 expedition. The RV Forker deployed ROV Sebastian to collect water samples. Instruments recorded fluid temperatures around 12.4 degrees Celsius. This moderate heat supports optimal microbial metabolic rates perfectly. Free-living bacteria float within the warm, nutrient-rich fluid plumes. Other microbes build thick, gelatinous biofilms on the rocky substrate. The most efficient energy capture occurs within symbiotic biological relationships. Rifsha-Pachyptila tube worms colonize the absolute youngest vent rock cracks. These giant worms lack a mouth, gut, or digestive tract. They rely completely on internal chemosynthetic bacterial colonies for nutrition. A specialized internal organ called the traphosome houses these microbes. The worm absorbs hydrogen sulfide through its bright red plumes. Hemoglobin molecules transport the toxic gas directly to the bacteria. In return, the microbes synthesize essential carbohydrates for the host. This internal farming allows rapid growth in otherwise barren environments. Costa Rican tube worms can grow up to 2 meters long. Their growth rates rank among the fastest of marine invertebrates. Scientists measured an annual length extension of 85 centimeters. This rapid biomass accumulation fuels the entire local deep ecosystem. When tube worms die, their decaying tissues feed numerous benthic scavengers. The older Galapagos rift vents feature declining tube worm population numbers. In stark contrast, the Costa Rica field shows explosive colonization. Beyond symbiosis, many distinct animals consume the bacterial mats directly. Swarms of grazing gastropods scrape the mineralized basaltic rocks constantly. Lepidodrylus limpets possess specialized radula teeth for this exact task. These tiny snails clear visible paths through the microbial forests. Their continuous feeding regulates the thickness of the bacterial biofilms. Biologists counted up to 400 limpets per square meter. This incredible density provides a massive food source for predators. Squat lobsters patrol the dangerous periphery of the venting fluid. These pale crustaceans use feathery appendages to filter the water. They catch floating clumps of bacteria dislodged by ocean currents. Nunidopsis polymorpha is a very common squat lobster species here. They maintain a precise, calculated distance from the hottest water. Thermal sensors in their antennae prevent fatal external heat exposure. The ambient seawater remains near a frigid 2 degrees Celsius. Moving just 10 centimeters can mean a 50-degree temperature difference. This extreme thermal gradient structures the biological community zone strictly. Energy flows upward to highly mobile secondary consumers and hunters. Pythogorid crabs navigate the dense tube worm clusters continuously without resting. They possess specialized, powerful claws for crushing hard limpet shells. These crabs also scavenge dead organisms near the active vents. Their blood contains hemocyanin to bind scarce dissolved oxygen molecules. This specific adaptation allows survival in highly hypoxic fluid plumes. Zooarcid fish weave through the tube worm tubes seeking small prey. These pink eelpouts consume small amphipods and vulnerable grazing snails. They exhibit highly reduced metabolic rates to conserve precious energy. ROV Jason captured high-definition footage of their unique hunting behavior. The fish ambush prey rather than pursuing them actively underwater. This patient strategy minimizes oxygen consumption in the deep sea. Apex predators visit the vent field from surrounding abyssal areas. Volcanoptopus hydrothermalis represents a specialized deep-sea benthic cephalopod species here. This completely pale, ghostly octopus lacks an ink sac entirely. Ink serves no defensive purpose in total, absolute oceanic darkness. The octopus hunts crabs using highly sensitive, tactile muscular arms. Its persistent presence indicates a fully mature food web structure. Comparing this site to the East Pacific rise reveals differences. The East Pacific rise features massive, towering sulfide chimney structures. Those tall black smokers host different biological assemblages entirely today. Alvanellid worms dominate the hottest zones of those mineral chimneys. The young Costa Rica vents lack these large mineral towers. Instead, warm water diffuses steadily through broad cracks in basalt. This specific diffuse flow creates a wider, more stable habitat. Organisms spread horizontally rather than climbing vertical, unstable mineral spires. The spatial biological distribution resembles a meadow rather than a forest. Biomass per square meter is slightly lower than mature sites. However, the overall biodiversity index is surprisingly high right here. Dr. Jorge Cortés documented 42 distinct benthic species during surveys. 7 of these discovered species were entirely new to science. This high endemism highlights the profound evolutionary isolation of vents. The nearest active vent field lies 400 kilometers away. Microscopic larvae must travel vast distances across barren abyssal plains. Deep ocean currents transport these fragile larvae between vent sites. Only a remarkably tiny fraction survive the journey to settle. The chemical composition of Costa Rica vent fluids is unusual. Dissolved silica concentrations are significantly lower than regional Pacific averages. Iron and manganese trace levels remain relatively depleted right here. Conversely, dissolved methane gas concentrations remain unexpectedly high and constant. This methane supports a distinct subpopulation of specialized methanotrophic bacteria. These specific microbes consume methane rather than toxic hydrogen sulfide. They form thick, white, stringy mats resembling scattered cotton fibers. Bathymodialus mussels host these methanotrophic bacteria inside their large gills. These symbiotic mussels dominate the cooler outer edges of the vent field. They attach securely to rocks using strong, flexible byssal threads. Their hard shells provide secondary solid substrates for other organisms. Polychaete worms construct fragile, branching tubes directly on the mussel shells. This process creates a microecosystem within the larger vent community. Energy cascades through multiple microscopic biological tiers in this zone. Ciliate protozoans graze continuously on the loose, floating methanotrophic bacteria. Nematode worms consume the engorged ciliates within the bottom sediment layer. This efficient microbial loop recycles precious nutrients completely within the system. Scientists monitor the remarkably rapid ecological succession at this site. The RV Atlantis returned to these exact coordinates in 2018. Researchers observed highly significant shifts in species dominance over time. Early colonizing tube worm populations had already begun to decline in density. Mussel populations were actively expanding into the formerly worm-dominated zones. This visible transition mirrors the natural, inevitable aging process of vents. As subterranean fluid channels shift, the local chemistry changes rapidly. A sudden drop in hydrogen sulfide favors the methane-reliant mussels heavily. Organisms must adapt constantly to these rapidly shifting chemical gradients. Some mobile species simply migrate to newly opened, active crustal fractures. Others perish completely as their specific chemical fuel source vanishes entirely. The dark seafloor is littered with empty, decaying white clam shells. Calyptargina magnifica clams require extremely high sulfide levels in the mud. Their empty, lifeless shells dissolve gradually in the acidic ocean water. Calcium carbonate dissolution takes many decades at this immense oceanic depth. These expansive shell graveyards mark the precise locations of extinct fluid flows. The extreme youth of this ecosystem challenges previous biological models. Evolutionary biologists study the rapid, ongoing adaptation of these distinct species. Advanced genetic sequencing reveals high mutation rates in local vent bacteria. Dr. Victoria Orphan analyzed microbial DNA extracted from these specific mats. She discovered entirely novel genes related to environmental heavy metal resistance. The venting fluid contains highly toxic levels of copper and zinc. Organisms must neutralize these dangerous metals to survive the harsh environment. Metallothionein proteins bind the absorbed heavy metals safely within animal tissues. This complex biochemical defense mechanism requires significant amounts of cellular energy. Despite these incredibly harsh conditions, life flourishes with truly remarkable vigor. The local biological density rivals that of shallow tropical coral reefs. Yet, the fundamental energy source remains entirely alien to terrestrial biology. This thriving ecosystem proves life can exist completely without the sun. Astrobiologists study this specific location as an analog for alien worlds. Moons like Europa might harbor very similar chemosynthetic deep vent ecosystems. The Costa Rica Vents offer a highly tangible model for this possibility. Understanding energy flow here expands the known parameters of life itself. Weighing the total biomass reveals the staggering efficiency of the food web. A single square meter can support over 30 kilograms of biological life. This massive weight consists mostly of dense tubeworm and muscle tissues. The dark water above the vents teems with microscopic, swimming zooplankton. Copepods gather in dense, swirling swarms near the warm thermal plumes. They feed continuously on the suspended, floating particulate organic matter. The year 2009 marked a significant research milestone. Scientists aboard the RV Atlantis reached the Costa Rica margin. They targeted a unique geological feature called the Jocko Scar. This depression lies at 9 degrees 7 minutes north latitude. The longitude is 84 degrees 50 minutes west exactly. Researchers deployed the autonomous underwater vehicle Sentry for initial surveys. Sentry glided over the seafloor at a precise calculated altitude. It utilized high-resolution multibeam sonar to map the rugged terrain. The resulting bathymetric data revealed unusual mounds and deep depressions. These structures hinted at active fluid expulsion from the crust. Scientists identified specific targets for closer visual inspection and sampling. The deep submergence vehicle Alvin prepared for its first descent. Alvin descended to a depth of 1,000 meters exactly. Dr. Lisa Levin observed the seafloor through the thick viewport. The submarine exterior lights illuminated a sprawling dense biological community. Researchers discovered a rare hybrid ecosystem at this specific location. It combined features of both methane seeps and hydrothermal vents. Scientists coined the term hydrothermal seep for this unique environment. The ambient water temperature measured a steady 2 degrees Celsius. Venting fluids emerged at approximately 15 degrees Celsius from cracks. This thermal anomaly confirmed active geological processes below the surface. Alvin's mechanical arms collected the first biological sediment push cores. Titanium syringes captured pristine water samples from the shimmering flow. The pilot carefully placed these samples into the insulated basket. Shipboard laboratories analyzed the collected fluid samples almost immediately. Dr. Victoria often focused on the microbial life within them. Mass spectrometers measured the precise concentrations of dissolved volcanic gases. The fluids contained high levels of methane and hydrogen sulfide. Isotope analysis revealed the thermogenic origin of these specific hydrocarbons. Deep subterranean heat was actively breaking down ancient organic matter. This chemical signature proved the extreme youth of the vent field. Geologists estimated the system's age at merely a few millennia. Further dives explored a geological feature known as Mound 12. This massive carbonate structure rose 30 meters above the seafloor. Alvin navigated carefully around the fragile towering biological mineral formations. In 2017, a new expedition returned to the site. The research vessel Forker brought advanced modern robotic deep-sea technology. Scientists deployed the remotely operated vehicle Sebastian for extended observations. Sebastian could remain submerged for over 72 hours continuously. High-definition 4K cameras captured unprecedented details of the vent fauna. Dr. Eric Cords directed the ROV operations from the control room. The team utilized a specialized underwater laser optical scaling system. 2 parallel green beams projected exactly 10 centimeters apart. This allowed precise size measurements of the observed deep-sea organisms. The ROV also carried a custom in-situ underwater mass spectrometer. This instrument analyzed fluid chemistry directly at the vent orifice. It eliminated the pressure changes associated with bringing samples up. Continuous observation required the installation of permanent deep-sea monitoring stations. Engineers designed specialized equipment for the harsh high-pressure ocean environment. They deployed continuous fluid osmo samplers near the highly active venting sites. These devices operate completely without any external electrical power source. They utilize osmotic pressure to draw water through fine capillary tubing. This mechanism collects fluid samples at a constant, extremely slow rate. The osmo samplers remain on the seafloor for 12 consecutive months. They preserve a year-long record of chemical fluctuations in the vents. Researchers also installed arrays of high-precision electronic temperature data loggers. These small titanium cylinders record thermal data every 15 minutes. The combined data sets reveal tidal influences on fluid expulsion rates. Transporting heavy equipment to these depths presents significant logistical challenges. The expedition team utilized free-falling benthic elevators for this purpose. These aluminum frames carry hundreds of pounds of sensitive scientific gear. Glass flotation spheres provide essential buoyancy for the eventual return trip. Acoustic release mechanisms secure the heavy iron sacrificial drop weights. Alvin loads the elevator basket with collected samples during the dive. This process maximizes the submarine's limited and valuable bottom time. At the end of the mission, a shipboard acoustic signal triggers release. The elevator ascends autonomously to the calm ocean surface above. A GPS beacon transmits its precise location for rapid shipboard recovery. Scientists quickly transfer the temperature-sensitive samples to refrigerated cold rooms. Local scientific collaboration plays a vital role in these international expeditions. Dr. Jorge Cortés from the University of Costa Rica joined the team. His expertise in regional marine biodiversity proved absolutely invaluable. The expeditions mapped extensive areas of the local exclusive economic zone. Researchers identified numerous new species endemic to these specific thermal vents. Taxonomic classification requires meticulous morphological and detailed genetic laboratory analysis. DNA sequencing laboratories aboard the ship processed organic tissue samples overnight. The resulting genetic data linked these populations to distant vent fields. Ocean currents transport microscopic larvae across vast empty abyssal plains. Dr. Cortés helped establish marine protected areas based on this data. The Costa Rican government recognized the ecological importance of the Joko scar. The research vessel Atlantis returned to the margin in 2018. The primary objective involved recovering the long-term deep-sea monitoring equipment. Alvin completed 21 successful dives during this highly specialized cruise. Pilots navigated back to the exact numerical coordinates of previous deployments. They located the Osmo samplers covered in a thin layer of marine sediment. The mechanical manipulators carefully extracted the delicate instruments from the mud. Scientists had also deployed autonomous time-lapse camera systems a year prior. These cameras captured high-resolution digital images every 4 hours exactly. The resulting photographic sequence documented dynamic changes in the biological community. Tube worm clusters shifted position in response to changing fluid flow. Bacterial mats expanded and contracted over the entire 12-month observation period. Mapping technology advanced significantly between the consecutive oceanographic research cruises. The team utilized multiple autonomous underwater vehicles simultaneously for wide coverage. These AUVs flew in tight formation 50 meters above the ocean bottom. They employed synthetic aperture sonar for millimeter-scale topographic surface resolution. The acoustic data generated highly detailed three-dimensional models of the mounds. Geologists identified microscopic fault lines intersecting the main mineral vent structures. These fractures serve as primary conduits for the heated subterranean fluids. The sonar also detected acoustic anomalies suspended in the dark water column. These anomalies represented dense plumes of methane bubbles escaping the seafloor. Acoustic Doppler current profilers measured the velocity of these ascending chemical plumes. The data improved complex mathematical models of global marine carbon cycling. Sampling the fragile biological specimens requires extreme mechanical precision and care. Biologists use specialized suction samplers attached securely to the ROV frame. This device functions like a gentle underwater vacuum cleaner for small organisms. It collects delicate animals without causing any structural or cellular damage. The animals travel through transparent tubing into rotating acrylic collection jars. Each jar contains a unique digital identification tag for accurate tracking. Researchers also deploy sterile colonization blocks near the highly active vents. These identical basalt cubes provide a clean blank substrate for new life. Scientists retrieve these heavy blocks after a specified 6-month incubation period. They analyze the precise sequence of microbial and macrofaunal colonization events. This experiment reveals how these young ecosystems established themselves initially. Modern deep-sea expeditions rely heavily on continuous real-time data integration. The research vessels feature sophisticated telepresence satellite command centers on board. Satellite links broadcast live high-definition video feeds to shore-based university laboratories. Scientists around the world participate in the deep dives entirely remotely. They provide immediate expertise on unexpected geological or rare biological discoveries. The ROV carries a comprehensive suite of advanced electronic geochemical sensors. These instruments include optical dissolved oxygen sensors and highly sensitive pH probes. The sensors transmit continuous digital data streams back to the surface ship. A specialized software program overlays this chemistry data onto the video feed. This allows researchers to correlate animal behavior with invisible chemical gradients. The precise mapping of these microhabitats is a primary scientific mission goal. The Costa Rica margin is a highly active and volatile tectonic zone. The massive Cocos Plate subducts beneath the adjacent Caribbean plate here. This immense geological friction generates frequent and powerful localized deep earthquakes. Scientists deployed a network of ocean bottom seismometers around the active vents. These instruments detect minute microtremors completely invisible to land-based monitoring stations. The seismic data correlates strongly with variations in hydrothermal fluid flow. Earthquakes can widen existing subterranean fractures or create entirely new ones. This physical movement alters the plumbing system of the entire vent field. The temperature loggers often record thermal spikes immediately following large seismic events. Understanding this dynamic relationship helps explain the transient nature of these ecosystems. The youngest vent fields are particularly susceptible to these sudden tectonic shifts. The deep submergence vehicle Alvin underwent significant mechanical and electrical upgrades recently. A new thicker titanium personnel sphere increased its maximum safe depth rating. The submarine can now reach 6,500 meters without structural failure. Improved high-definition external cameras capture wider cinematic angles of the seafloor landscape. Enhanced robotic manipulator arms offer greater mechanical dexterity for complex sampling tasks. These specific upgrades proved essential during the latest Costa Rica margin surveys. Pilots could maneuver much closer to the fragile crumbling carbonate mineral chimneys. They collected delicate mineral flanges without disturbing the surrounding physical vent structure. The submarine's advanced lithium battery system extended the average daily dive duration. Scientists gained 2 additional hours of highly valuable bottom observation time. The preservation of collected deep-sea samples follows a highly rigorous scientific protocol. Technicians flash freeze delicate biological specimens in liquid nitrogen immediately upon surface recovery. This rapid freezing stops all cellular degradation and preserves fragile RNA molecules perfectly. The Costa Rica margin represents a unique geological anomaly. Scientists consider this the youngest hydrothermal field on Earth. Most vent systems exist along active mid-ocean spreading ridges. The East Pacific rise produces vents through rapid divergence. Tectonic plates there separate at 15 centimeters per year. The Mid-Atlantic ridge moves at a much slower pace. It separates by only 2 centimeters every single year. Those traditional ridge systems rely on shallow magma chambers. The Joko Scar vents operate under completely different mechanisms. This field formed through subduction rather than plate separation. The Cocos Plate slides beneath the Caribbean Plate here. This tectonic collision creates immense friction and crustal fracturing. Seawater penetrates these fresh fractures along the continental margin. Geologists estimate the Dorado outcrop is remarkably young. Its hydrothermal circulation began less than 1 million years ago. Other global vent fields boast much older geological histories. The Lost City field in the Atlantic is older. Carbonate chimneys there have grown for 30,000 years. Costa Rican vents feature much smaller and newer mineral deposits. Fluid temperatures here average around 10 to 20 degrees Celsius. This contrasts sharply with the Mariana Trench hydrothermal vents. Mariana black smokers routinely exceed 300 degrees Celsius. The Endeavour segment in the Pacific is similarly extreme. Costa Rica offers a rare glimpse into early vent formation. Researchers observed the initial stages of chemosynthetic ecosystem development. This youthful environment provides a baseline for global comparisons. Costa Rica's Joco Scar is located much closer to land. It sits just 30 kilometers off the Pacific coastline. This proximity makes logistical planning for research expeditions easier. Most mid-ocean ridges require weeks of transit time to reach. The East Pacific Rise spans thousands of unbroken kilometers. It bisects the Pacific Ocean floor like a massive seam. Volcanic activity there is continuous and highly energetic. Lava flows frequently pave over older vent structures. The Costa Rica margin lacks this massive volcanic resurfacing. Instead, fluid flows through faults created by tectonic bending. The subducting plate cracks as it bends into the trench. These bend faults provide deep pathways for seawater circulation. These young vents hold clues to early biological evolution. Many scientists believe life began in similar hydrothermal environments. The primordial ocean lacked free oxygen and protective ozone. Surface waters suffered from intense ultraviolet solar radiation. Deep-sea vents offered a stable refuge for early molecules. Dr. Michael Russell proposed the alkaline hydrothermal vent theory. His model focuses on natural proton gradients across minerals. Costa Rican seep fluids interact with exposed mantle rocks. This geological interaction triggers a process called serpentinization. Olivine minerals react with seawater to produce hydrogen gas. This hydrogen acts as a crucial chemical energy source. It reduces carbon dioxide into simple organic hydrocarbon molecules. Abiotic methane forms without any biological intervention here. These chemical reactions mimic the dawn of cellular life. Iron-sulfur clusters form naturally within the vent rock matrices. These mineral structures resemble the active sites of modern enzymes. Early metabolic pathways likely utilized these exact inorganic catalysts. Dr. William Martin studies the last universal common ancestor. His genetic research points directly to a hydrothermal origin. The first organisms required constant chemical disequilibrium to survive. Vent fluids provide this necessary imbalance through thermal gradients. Porous rocks act as primitive cell membranes for chemical concentration. Nucleotide synthesis could occur within these microscopic mineral chambers. RNA molecules might have polymerized on these catalytic surfaces. The Costa Rica margin serves as a living laboratory. Biochemists sample these precise fluids to test origin theories. They measure the isotopic signatures of dissolved carbon compounds. The data helps reconstruct the timeline of Earth's biosphere. Greigite is an iron sulfide mineral common in these vents. Its crystal lattice is identical to the core of ferredoxin. Ferredoxin is an ancient protein essential for cellular respiration. This structural match strongly supports a mineral origin for metabolism. Amino acids can form spontaneously in these heated chemical mixtures. Laboratory simulations successfully produce peptides under vent-like conditions. The high pressure prevents water from boiling despite extreme heat. This supercritical fluid state acts as a powerful chemical solvent. It extracts transition metals from the surrounding basaltic rocks. These metals act as catalysts for complex organic reactions. The gradients of pH and temperature drive these reactions forward. Life is fundamentally a process of managing electron transfers. Vent chimneys are natural batteries conducting continuous electrical currents. Exploring these depths requires highly specialized engineering solutions. The water pressure at 3,000 meters is immense. It exceeds 300 atmospheres of crushing physical force. Standard equipment would instantly collapse under this extreme stress. The human-occupied vehicle Alvin underwent significant recent upgrades. Engineers installed a thicker titanium personnel sphere for safety. Titanium provides optimal strength while maintaining critical buoyancy. The vehicle utilizes syntactic foam to float in dense water. This foam contains millions of microscopic hollow glass spheres. External sensors face severe challenges from the vent chemistry. Hydrothermal fluids are highly corrosive to standard marine instruments. Some localized fluid pockets possess a pH of 2.8. This acidity rivals concentrated industrial vinegar or stomach acid. Probe housings must utilize specialized alloys like Hastele. Remotely operated vehicles like JASON perform extended benthic surveys. JASON connects to the surface ship via a fiber optic cable. This umbilical tether transmits high-definition video and telemetry data. Managing this tether in strong deep ocean currents requires skill. Pilots must avoid wrapping the cable around jagged mineral spires. Autonomous underwater vehicles map the Costa Rica margin independently. The robotic sub-sentry programs its own complex grid patterns. It maintains a precise altitude of 5 meters above the bottom. Navigation without global positioning relies on acoustic transponder networks. Sound waves travel predictably through the dense saltwater medium. Battery technology limits the duration of these autonomous missions. Lithium-ion pressure-tolerant batteries provide about 40 hours of power. Data retrieval occurs only after the vehicle breaches the surface. Hydraulic fluid powers the robotic manipulator arms of the vehicles. These fluids must operate smoothly at near-freezing ambient temperatures. The deep ocean hovers around 2 degrees Celsius globally. Lighting is another massive engineering hurdle for deep-sea exploration. Water rapidly absorbs the electromagnetic spectrum of visible light. Red light disappears within the first few meters of depth. High-intensity diode arrays illuminate the pitch-black vent fields. These lights require complex thermal management to prevent overheating. The cold seawater provides natural liquid cooling for the arrays. Data storage demands are immense for modern oceanographic surveys. High-resolution cameras record terabytes of video on each dive. Scientists catalog this footage frame by frame back on shore. These vent fields accumulate significant concentrations of valuable minerals. polymetallic massive sulfides form as hot fluids hit cold seawater. Dissolved metals precipitate instantly into solid particulate matter. Over millennia, these particles build massive sulfide mounds. The deposits contain high grades of copper and zinc. Trace amounts of gold and silver also exist here. Rare earth elements bind to the mineral matrices over time. These elements are crucial for modern electronic manufacturing. Neodymium and dysprosium power advanced wind turbine magnets. Tellurium is essential for manufacturing efficient solar panels. Geologists map these deposits using electromagnetic induction sensors. They measure the electrical conductivity of the seafloor crust. Biological resources present another frontier of deep-sea value. Extremophile bacteria possess unique genetic adaptations for survival. Their enzymes function flawlessly under extreme heat and pressure. Historically, vent bacteria completely revolutionized molecular biology techniques. The Taq polymerase enzyme originated from a similar extremophile. This enzyme enables the polymerase chain reaction for DNA testing. Pharmaceutical companies actively research these deep-sea biological communities. Marine bioprospecting searches for novel antibiotic and antifungal compounds. Microbes fighting for space produce potent chemical defense mechanisms. These secondary metabolites show promise in treating human diseases. Researchers recently isolated new molecules from deep-sea marine sponges. These compounds demonstrate targeted activity against specific cancer cells. The genetic wealth of the Costa Rica margin remains largely untapped. Vent massive sulfides offer much denser concentrations of valuable metals. A single vent chimney can weigh hundreds of metric tons. Mining companies design massive robotic cutting machines for this task. These machines resemble terrestrial coal mining equipment with specialized tracks. They must grind the solid sulfide rock into a dense slurry. Pumps then push this heavy slurry up a vertical riser pipe. This riser pipe extends 3 kilometers to a surface vessel. The engineering required to maintain this flow is staggering. Pipe blockages could halt operations and cost millions of dollars. Bioprospecting requires much less invasive scientific extraction methods. Scientists only need a few grams of biological material. They sequence the microbial DNA directly from these small samples. Synthetic biology allows them to recreate the enzymes in laboratories. This eliminates the need for continuous harvesting from the seafloor. Companies commercialize specialized enzymes from these hydrothermal vents. These enzymes improve the efficiency of industrial ethanol production. Protecting these fragile environments presents a complex global challenge. Deep-sea mining interests look toward vent fields for resources. The International Seabed Authority regulates mineral extraction beyond national jurisdictions. Costa Rica controls the economic rights within its exclusive economic zone. Mining operations would severely disrupt the benthic ecosystem. Extracting sulfide mounds destroys the primary habitat for endemic species. Heavy machinery generates massive clouds of suspended sediment. These benthic plumes travel for miles on deep ocean currents. Settling sediment smothers delicate filter-feeding organisms like glass sponges. The particulate matter clogs the gills of local gallethide crabs. Recovery rates for deep-sea ecosystems are incredibly slow. Cold temperatures and limited food restrict biological growth rates. Some deep-water corals take thousands of years to mature. A single mining event could erase millennia of ecological development. Marine biologists advocate for strict international conservation frameworks. The Costa Rica margin influences global climate systems deeply. Hydrothermal vents release intense thermal energy continuously into seawater. This localized heat alters deep ocean circulation patterns significantly. Bottom water temperatures rise near the active mineral chimneys. Warmed fluid rises rapidly through the dense water column. This upward movement creates microcurrents along the dark seafloor. These currents feed into the larger planetary thermohaline circulation. Global ocean conveyor belts rely on these thermal gradients. Vents contribute measurable heat to this planetary circulatory system. Chemical exchanges here also impact the global carbon cycle. Chemosynthetic bacteria consume dissolved carbon dioxide very rapidly here. They convert inorganic carbon into organic cellular biological material. This specific biological process sequesters vast amounts of carbon. Microbial mats trap carbon within their complex physical structures. Dead organisms eventually sink into the surrounding soft sediment. Their carbon remains buried deep in the oceanic crust. Mineral precipitation further aids in long-term global carbon storage. Calcium carbonate formations lock away dissolved greenhouse gases permanently. Geochemical reactions alter the surrounding seawater local alkalinity levels. Higher alkalinity increases the ocean capacity for absorbing carbon. Scientists study these vents to model future climate scenarios. Dr. Lisa Levin researches these deep ocean carbon sinks. Her data shows significant biological carbon fixation rates occurring. The young vent field offers a pristine ecological baseline. Researchers measure carbon uptake at 9 degrees north latitude. They deploy benthic chambers to track benthic gas exchange. Sensors record carbon dioxide levels every 10 minutes exactly. The data reveals highly efficient microbial carbon processing capabilities. This efficiency surprised marine biogeochemists during recent underwater surveys. The Costa Rica vents act as biological carbon filters. They process greenhouse gases escaping directly from the mantle. Without these microbes, more carbon would enter the seawater. Dissolved carbon lowers the overall pH of the ocean. Ocean acidification threatens delicate marine ecosystems worldwide right now. Vent bacteria mitigate localized acidification near the active fissures. Their metabolic pathways stabilize the surrounding chemical environment perfectly. Iron released from vents fertilizes the upper ocean layers. Upwelling currents carry dissolved iron toward the ocean surface. Phytoplankton rely on this iron for cellular photosynthesis processes. Massive phytoplankton blooms absorb atmospheric carbon dioxide very efficiently. The Costa Rica vents thereby influence surface climate dynamics. Deep sea heat flux also affects regional weather patterns slightly. Warming bottom waters change the density of ocean layers. Changes in density drive vertical water mass mixing currents. This mixing distributes dissolved oxygen throughout the Pacific Basin. The entire planetary biosphere connects to these deep fissures. Earth operates as a highly integrated thermal biological machine. The East Pacific Rise acts as a massive engine. Deep ocean currents sweep across these heated volcanic ridges. Cold Antarctic bottom water meets the intense geothermal heat. This collision creates complex thermal layers near the seabed. Nutrient-rich bottom waters get pushed upward by the heat. These nutrients include silicates essential for diatom shell formation. Diatoms form the base of the global marine food web. Therefore, deep vents directly support surface pelagic fish populations. Whales feed on the krill nourished by these upwellings. The connection between the abyss and surface is undeniable. Carbon cycling involves highly specialized enzymatic chemical reactions here. Ribulose bisphosphate carboxylase plays a major role in fixation. This enzyme allows bacteria to build complex sugar molecules. These sugars sustain the entire local hydrothermal vent food chain. Energy transfers efficiently from the crust to the biosphere. Many scientific questions remain about this young vent field. The precise timeline of microbial colonization remains largely unknown. Scientists want to understand early ecosystem development phases better. Dr. Victoria often plans future expeditions to this site. Her team will study archaea using stable isotopic tracing. They aim to map the entire microbial food web. New technologies make this ambitious research possible today. Autonomous underwater vehicles map the seafloor with green lasers. These robots operate entirely without direct human remote control. They navigate complex chimney structures using advanced acoustic sensors. High-resolution sonar creates millimeter-scale topographic seafloor digital models. Researchers can identify microscopic vents smaller than a teacup. Artificial intelligence processes the massive sonar datasets extremely rapidly. Machine learning algorithms detect subtle geological formation changes automatically. They highlight new microcracks forming in the basaltic crust. Next-generation submersibles will carry advanced miniature mass spectrometers. These instruments analyze fluid chemistry in absolute real time. Scientists will not need to bring fragile samples surface. In situ analysis prevents pressure changes from altering chemical fluids. The Woods Hole Oceanographic Institution designs these innovative tools. Engineers test titanium housings for extreme hydrostatic pressure resilience. Future missions will deploy long-term seafloor sensor observatories permanently. Cabled networks will provide continuous power to benthic sensors. Fiber optic lines will transmit data instantly ashore. Oceanographers will monitor vent temperatures from their land laboratories. They will watch biological succession happen over several decades. The Schmidt Ocean Institute scheduled a return scientific voyage. Their research vessel Forker will arrive next spring season. They will deploy a remotely operated vehicle named Sebastian. Sebastian features a highly customized robotic biological sampling arm. Soft robotic grippers will collect fragile biological specimens safely. These grippers use fluid pressure to close very gently. They capture delicate tube worms without causing tissue damage. Geneticists will sequence the DNA of these captured specimens. They hope to find undiscovered metabolic chemical pathways inside. New microbial enzymes could revolutionize industrial chemical manufacturing processes. Pharmaceutical researchers look for novel antibiotic compounds down here. Extreme environments often produce unique chemical defensive molecules naturally. Bacterial competition drives the rapid evolution of these compounds. The young vent field represents a massive genetic goldmine. Every deep expedition yields species completely new to science. Taxonomists struggle to classify the rapid biological discoveries constantly. Geologists plan to drill into the surrounding oceanic crust. They want to sample the subsurface biosphere directly below. Microbes live deep within the porous basaltic rock layers. This hidden biosphere might contain immense biological cellular mass. Drilling ships use diamond-tipped bits to penetrate the seafloor. They extract cylindrical rock cores for strict laboratory analysis. These cores reveal the geological history of the margin. Isotope ratios in the rock indicate past temperature fluctuations. Scientists reconstruct the ancient climate of the Pacific Ocean. They compare past vent activity with current thermal measurements. This data helps predict future tectonic plate movements accurately. The subduction zone dynamics remain a major research focus. Acoustic modems will transmit data through the water column. Surface buoys will relay this information to orbiting satellites. Researchers in landlocked cities will study the deep sea. Virtual reality will allow scientists to walk the seafloor. High-definition stereoscopic cameras capture the vent field in 3D. Geologists can measure chimney growth rates using these models. Photogrammetry software aligns thousands of individual underwater photographs perfectly. This creates a digital twin of the Costa Rica Vents. Scientists can simulate fluid dynamics within this virtual environment. They model how toxic minerals disperse into the ocean. Understanding plume dynamics helps predict larval dispersion across oceans. Larvae of vent species travel hundreds of miles adrift. They ride deep ocean currents to find new fissures. Genetic tracking will map these complex migratory larval pathways. Environmental DNA sampling detects species without capturing them physically. Water samples contain microscopic cellular debris from local organisms. Sequencing this debris reveals a complete biodiversity census quickly. Deep-sea exploration constantly challenges our fundamental understanding of life. These ecosystems exist completely independently of solar energy input. They rely entirely on the internal heat of Earth. This fact shifts our perspective on planetary biology entirely. Habitable zones may exist on distant icy planetary moons. Europa and Enceladus might harbor similar hydrothermal vent systems. The Costa Rica margin serves as an astrobiology analog. Studying this young field prepares us for deep space. Yet this fragile ecosystem faces unprecedented human industrial threats. Deep-sea mining companies target active hydrothermal vent fields globally. Chimneys contain high concentrations of valuable rare earth metals. Copper, zinc, and gold precipitate from the superheated fluids. Mining operations would destroy the delicate mineral chimney structures. Heavy machinery would crush the thriving microbial benthic mats. Sediment plumes would choke the surrounding delicate filter feeders. The noise pollution would disrupt marine mammal acoustic communication. Protecting these nascent ecosystems is critically important for science. The International Seabed Authority regulates ocean floor mineral resources. Conservationists advocate for strict deep-sea mining environmental bans everywhere. They propose establishing marine protected areas around active vents. The Costa Rica Dome requires special legal conservation designation. Its status as the youngest field makes it uniquely vulnerable. Once destroyed, these specific communities might never fully recover. The geological conditions that form them are highly temporary. Tectonic plates shift constantly along the active subduction zone. The fluid pathways will eventually seal themselves completely shut. We must study them while they remain chemically active. Preservation allows future generations to observe this natural wonder. Marine biologists monitor the site for illegal trawling activities. Deep water fishing nets can easily snag on the chimneys. A single net can topple a decade of mineral growth. International treaties attempt to limit bottom trawling practices globally. Enforcement remains difficult in the vast open ocean expanse. Satellite tracking helps identify vessels entering protected coordinate zones. Public awareness drives the creation of new ocean sanctuaries. Documentaries bring these hidden worlds into our living rooms. Knowledge fosters a deep desire to protect the unknown. Polymetallic sulfides form the core of these hydrothermal chimneys. These minerals take thousands of years to accumulate fully. Industrial extraction would erase this geological history in hours. The resulting sediment plumes would travel for many miles. Suspended particles clog the delicate gills of deep-sea organisms. Filter-feeding sponges cannot survive in highly turbid water conditions. Bioluminescent communication becomes impossible in the cloudy, disturbed water.